All right, so today we continue on with lesson 6.2. So take a look at the problem of the day. You might want to pause the video and solve it. It's important because it leads us into what we're doing today with adding and subtracting radicals. All right, so to continue on from previously, we haven't actually taken a look yet at adding or subtracting. Now, if you remember back from the previous chapter, or chapter 4 as well, 4 and 5, that when you add or subtract radicals, they have to have the same root. So do you see how in letter A they are both the fourth root? And they have to also have the same number inside the root. So they both have what? Fourth root of 10. Fourth root of 10. If they have the same radical and the same number inside of it, all we have to do is add or subtract the coefficients. Now if you notice for the first part, do you see how there is no number? Can't we write that as a 1? It's understood to be a 1. So 1 plus 7 is 8. And then you attach the fourth root of 10 to it. And that's my answer. So 8, fourth root of 10. All right. And as you can see, I also write must be alike. All right. Now, what if it looks like in this form? I don't have the root or radical, right? I have a rational exponent, so 8 to the 1/5. Same idea. 2 plus 10 is 12. And then just rewrite 8 to the 1/5. That's my answer. If you don't like the rational exponent, isn't that the same as saying this? So it's really a personal choice here. If you're okay with converting between both types, that's fine. If you would want to rewrite it as the fifth root of 8 like this, you can do that as well. Same idea though. All right. Now, it's great and fine if I give you all of them that have like terms, like roots or like rational exponents. But what if I don't? Let's look at see how we would solve that. Cube root of 54 minus cube root of 2. If you notice, 54 and 2 are not the same numbers, so I can't immediately go to subtract them. What I have to do with 54, if you remember the product property, I'm able to split up 54 into two numbers that are cube roots. Let's just rewrite the cube root of 2 over here. Bring that over. So what you might want to do, like we talked about in the last part of the lesson of 6.2, go to your assignment 1 with that table we filled out, look at your perfect cube column, and ask yourself, how can I split up 54 with one of the numbers being a perfect cube? You should actually get 27 times 2. Now cube root of 27 is 3 cube root of 2 minus cube root of 2. Now what number is in front of this again here? 1. Remember, when there's no number, it's understood to be a 1. 3 minus 1 is 2. And then attach the cube root of 2. So by using the product property and simplifying cube root of 54, I now have a common root and like terms that I could subtract. All right, so let's take the same idea, and as you see here, we had just all numbers. Let's apply it to where you have variables as well. So in A, perform the indicated operation for example 5. You see that square root of w and square root of w are the same. So we're allowed to add the fractions. 1/5 plus 3/5 is 4/5. And attach the square root of w. So 4 over 5, let's fix the 5 there. 4 over 5, square root of w is your answer. Here's another example with rational exponents. And make sure it's all the same. We have what? X, y to the 1/4, xy to the 1/4. So they are like terms, all right? The x doesn't have a root around it or an exponent like a fraction. That's okay. 3 minus 8 is -5. And then attach the xy to the 1/4. That's my answer. All right, so let's look at C. C is like example 4C on the previous slide. What happens if what's inside the root is not exactly the same? Did you see I have 9w to the 5th and w cubed? Well, we can split it up just like the last one. Let's sort of take a look at how we split up with the variable. If we go back for a second, you see that 54 was split up into a nice perfect cube and what's left over. So we're going to follow that same pattern, and I think I'm going to write up here for more room. So for the first piece, let's write our two square root symbols. We're going to split this up. All of my nice perfect squares are going to go here, and whatever's left over is going to go here. So let's assess from the beginning. Is 9 a perfect square? Yep. So we could put the 9 there. And I have w to the 5th. If I have a square root, I want multiples of 2 because it's a square root. So I have what? 2, 4. I have 4 w's that will go in this first one. This first root is all my perfect squares. What's going to get rid of the root in the end? Just like if we go back, 27 is a perfect cube, it got rid of the root. So you're trying to split it up into 2 parts here. Now what's left over? If I had 5 w's, 4 go here. Well, doesn't that mean that we have 1 left over in the other parenthesis, or in the other root? To write the minus w, we're going to do the same thing again with 2 roots. All right. I have w cubed. I want pairs of 2 because it's a square root. So we could put 2 w's here, w squared. And then I have 1 w left. So once again, this first root here and the first root here, we want perfect square roots where the root is going to go away. Now, square root of 9 is 3. W to the 4th to the 1/2 is just a square. And if that confuses you, I want to add something here for a second to this one. This is the same as saying 9w to the 4th to the 1/2, right? What I am doing with the root, because of my exponent rules, 4 times 1/2 is 2. That's where I'm getting the 2 here. I like to remember with the root I'm dividing. So 4 divided by a square root is 2. Does that make sense? If you like to rewrite it as a rational exponent, you can. That's why you also get 2. But I like to remember that I'm dividing those numbers out. Now for this one, w squared, squared divided by 2 is just a w. Because once again, it's the same as saying this. Two times 1/2 is just 1, right? I do 2 divided by 2. Let's simplify here. 3w squared root of w is all the same. Now w times w is w squared, right? Root of w. Now they both have w squared. They both have square root of w. Don't forget that this is a 1 here. 3 minus 1 is 2. And then attach the rest. W squared square root of w. That's my answer. Now we will revisit C on our last and final example here on the next slide. All right. So last example, example 6, write the expression in simplest form, use multiplication property of exponents. All right. So you see I have a 5th root. Once again, using the product property, I'm going to split it up into 2 big roots. The first root on the left is going to have all my nice perfect 5th powers because it's a 5th root, right? And the one on the right is going to have everything else that's left over. So let's start from the beginning. Is 4 a perfect 5th root? No, it's not a nice number, so it goes in the leftover root. All right, let's assess a to the 8th. How many a's can I bring in to that first one? 5, right? We want multiples of 5 here. You might be saying, well, why multiples of 5? Because it's a 5th root. So if I take 5 a's here, how many are left over? 3. All right, so 3 a's go over here. Now let's look at b. How many multiples of 5 can I get with b? 5, 10. So 10 b's go here. I'm left with 4 over here. Now c's to the 5th. I could put all 5 here. And then I have no leftovers here. So once again, this first root is going to be all my perfect fifths, 5, 10, 5, right? And the second root is going to be what's left over. All right, so now we're going to divide what's the exponents are in here to here, right? 5 divided by 5 is 1, so I just get a to the first, or just a. 10 divided by 5 is 2, so I get b squared. 5 divided by 5 is 1, or just a c. And whatever's left over just gets rewritten in the second root. A little 5th root there, and that's our answer. All right. So to apply that same thing for the last one, let's actually use the quotient property and split them up into 2 roots. So the last one here. We know with the quotient property, we want the root and the denominator to go away. And we know how to do that is whatever you multiply the bottom by, you're going to multiply by the top as well to keep it true. All right. So remember, with the cube root, it's slightly different, or any root other than a square. Think to yourself, I have 8 y's. I need multiples of 3. Why multiples of 3? Because it's a cube root. So how many y's do I need to get the next, like third kind of number that will work out evenly? Shouldn't I just add 1? Now you could go higher, but then that's going to be more work to simplify. But once again, why I want 1? I want the next multiple of 3. 3, 6, 9. We want the next multiple bigger than 8. 3, 6, 9. So we need 1 y on top and bottom. Whatever you do at the bottom, you got to do the top. So that leaves us with the top is just the cube root of xy over the cube root of y to the 9. Remember, when you multiply, you add exponents. 8 plus 1 is 3. So let's rewrite the top again. Cube root of xy can just stay like that. Over 9 divided by 3 is 3. So remember, we divide them. So it's y cubed in the denominator. And that's our final answer. All right, so homework, problem of the day, make sure you write it out and give yourself an explanation. And then problem 2, complete the following problems, just numbers 1 and 10.